Good evening. We will get started with today's session. So today we are doing the revision and some problem solving of week 5 lectures of the course User-Centric Computing for Human Computer Interaction. I'm Spruha Satavlekar. I'm the PMRF TA working with the NPTEL team in this course, and I have tried to initially give a little bit of simplified version of problem solving and revision for the previous weeks. All the 4 lectures have been shared over YouTube, and while we post this video, we will also connect the previous 4 video links to it. So we'll start with the week 5 content. So before we go into the week 5, let's recall what we did from the 4 weeks, previous 4 weeks. So we spoke a lot about you making the graphical user interfaces user centric. Basically understanding what the user performs, how they perform it, and making the GUI experience or layout experience easier for them. So actually by making that easier, we mean to increase the usability of our system. And if we recall what is usability, it was defined by Nielsen with these 5 pointers: learnability, efficiency, memorability, error, satisfaction, and utility. So what we try to do, the main focus is to increase our users' learnability, make our interfaces quick and easy to learn. Then efficiency, that is make the user finish the tasks that they want faster, so that they can perform multiple tasks in a good pace. Third one is memorability. So once a user has used your platform or the application that. Okay, yeah, sure. So we will be conducting the week 6 material problem solving in the next 7 to 9 timeline on next Tuesday. So this Tuesday we will focus on week 5 only, because every week we take up the previous week's assignment, so that the current assignment which is due, you'll be prepared to solve it. So that's why I'm taking the week 5 today, and we will conduct for week 6 next week also. Every week we will be conducting. So yeah, I was talking about the memorability. So memorability is once a user has gone through your system, while they visit again, they shouldn't have to recollect all the things, make it cumbersome for them to recollect how to use your user interface. So that's the factor about memorability. So you make your GUI memorable, easy to recollect. And error is a factor where we try to reduce the error. So the user might be might should find it easier to navigate without making errors. So the user interface should also be designed in such a way that it doesn't naturally cause the user to create errors, and it also allows the user to be back recover from the error. So that's another factor in error. The last 2 factors are satisfaction. So when the user has come to your to visit your user interface, they have certain goals while they perform some actions on their user interface. So we have to give them the feedback that their action has been performed, not been performed, and their intended goal has been satisfied or not. We went through the gulf of evaluation and execution in one of the weeks previously. So this user satisfaction is integral in increasing the usability and utility, that is the basic functionality that the user wants out of the system. So considering these, today we are going to talk about the computational models. So today's week has been, the week prior to this, week 5, is a lot more about computing than the previously theoretical sessions that we did. So uh, this is just keep in mind that our aim is for making this our system user interfaces usable and more user friendly in a simple term. So we spoke about user-centric graphical user interfaces. A main point about user-centric graphical user interfaces is the WIMP way of expressing the screen. So there are windows, icons, menus, and pointers about which we will be considering the user actions around them. So this kind of full form has been asked in assignments previously also. Maybe next assignment or exam, this full form might be really useful. Next we have done the Fitts law. So last lecture in the week 4, we went through some of the classical models of user centric computing. So within those, we will recollect this Fitts law because for the fifth lecture series, 50 weeks lecture series, this Fitts law comes up a lot of times. So what is Fitts law? It is about the acquiring a target, and it was about the one dimensional view of the target acquisition. Actually, Fitts law was modeled in order to talk about any target acquisition. So there is a target object, you want to hold it in your hands physically. So that was the initial concept behind the Fitts law. In the computational world, it came across as one dimensional picking up or pointing at a particular object. So we last week we did the this model in which Fitts law explains the task difficulty in terms of index of difficulty. So the index of difficulty is the measure for this target acquisition. So what it says is, if a target of width say W is placed at a distance of D from the person or from the pointer, actually from the pointer, then the amount of difficulty associated with its acquisition or pointing towards it is given by this equation in terms of the log. Okay, so that's a derivation and all we have done last week. I will also add a link to it when I post this on YouTube channel so that you can refer to the derivation. So just for the time being, for this today's lecture, it will be beneficial to remember that this D represents the target's distance for us, and this W represents the width of the target. So imagine your laptop screen or your mobile phone screens, and imagine your pointer. So it might be your finger, it might be a touchpad that you are using, or it could be a mouse pointer that you are using to access this material. You will be performing a lot of movements, right, where to click on something and then perform some action. So this clicking action itself involves some type of difficulty for you, and that is modeled with this. Initially, wherever your pointer is placed, the next position's distance from that pointer place is the D, and the point that you want to click, its width, is known as W. What happens is, this initial Fitts law, that is only modeled for the one dimension, so that's why it only considers the width of the target. Okay, so it's basically like if the target is this much wide, it is easier for you to pick it up than it being smaller. So that's the idea behind this W. When we go from 1D to 2D, what we will do is we will consider more dimensions of the target. So we will not only speak about the width, we might also need to speak about the height of the target. So initial position of the we will talk about this initial position of our pointer on the screen. This is the desired box where I want to click. So now what I want to consider about the difficulty of this task is this distance up to which I want to move, and then I want to consider the height and width of this entire block that I want to click on. Now, uh, translating the Fitts law of one dimension to two dimension is very easy in terms of thinking like vectors in physics that we have studied previously in our schools or our colleges or junior colleges. So what do we do is we don't speak in terms of height and width initially. We think about this in terms of amplitude, that is the distance vector or the length of this arrow vector, and also consider the direction of this arrow. So this block could be here, this block could have been here also, so the pointer might have to go like this. So how to model this? We consider the amplitude and the direction. So trying to reduce the amplitude, this is the bivariate pointing model. It is again Fitts law only, but in bivariate pointing model we consider these two dimensions. One is the amplitude, that is the length of that the pointer has to traverse to reach the target in any direction, and then the second one is the directional pointing, which can be given by theta. So if you recollect from the trigonometry part, we can model any location on the two-dimensional plane based on this amplitude and the direction pointer. So when we want to try to reduce the error, we try to reduce the error in terms of amplitude error reduction and directional error reduction. So this law was given by this Fitts law was refined by Zai in 2003. So it is pretty recent, and ACM 6CAC is the CHI is the conference about human computer interactions. So it was presented in 2003 over there. This model basically now incorporates this width factor as well as this height factor. And initially we have seen previously, if we go here we just saw the width factor in the index of difficulty being considered, and now we see the height factor as well. So because there is another dimension, there is another constant associated with this dimension naturally. A and B, previously we have seen the A and B being empirically what were the initially found the empirical values of these A and B. So now we can again there has been empirical research about what could be these values. So large number of trials have been conducted, and it has been found that these values of this A, B and C are these for this equation. Now just for the purpose of preparing for examination or purpose of preparing for assignment, I don't think these values will be asked to you. So this is not essential to remember. Only thing is get an idea from these values what would be important for us. So this minus 50 to 200 for A, this is this constant. This T represents the task time that you do, the task acquisition time that you require to acquire this target. So it is basically kind of inversely proportional to the task difficulty. If the task is kind of proportional to the task difficulty. If the task difficulty is higher, you would require more time. If task difficulty is lower, you would require less time to perform this action. So that's the relationship between the ID and the T. T is the turnaround time of this action that we want to perform of task acquisition. So this A, B and C are the constant values. Depending upon various users, these may vary between this given value sets. D is the distance. Again, D is the distance of the target to be acquired. W and H are the width and height of the target. Similarly, in terms of 3D pointing model, this is again another addition to the previous model. So here initially we have seen this much. Now we have another constant and another letter of length, another dimension of length to consider. So basically T is the movement time, as I told before. D is the distance between the current hand position and the target. L the length of the target, height of the target, and the width of the target. So it's just uh, I have I did not include the derivation for the today's revision because it might be a lot too much to take in within 2 hours. So the lecture has a very good explanation of how this has been derived and what kind of assumptions lead to this derivation. All right, so I have not covered that in today's session. Again, these are the values for C1, C2. For the this is the initially we talked about this directions, right? Directional pointing. So direction is given by theta. So same theta is here. Okay, this is for directional pointing. So suppose the target is across the, just to acquire the target, if I want to move only horizontally, it might be theta is 0 degrees. If to acquire the target or reach the point new target, I want to go like this vertically, only vertical movement, then the theta would be 90 degrees. And if I want to traverse like this, then the theta would be 45 degrees. Empirically, a lot of trials get conducted for multiple users for the task, and then these values get calculated. We have gone through how they get calculated in the last lecture, and towards the end we did some revision of this. Yeah, so definitely the formula are not required to be remembered for exam purpose. So there will be no, usually in NPTEL exams there is no requirement of calculation for you. So these are basically but this question might be asked. So this formula is given, what does L represent? Or maybe not even the formula is given, you might be asked what is D in the Fitts law. So some kind of this question might for 3D pointing model. So these kind of questions would be asked about the meaning of this formula, the initials used in this formula. So the actual calculation or the formula are not asked in the examination. Your conceptual understanding and your functional understanding of this model will be asked, and also the purpose of why this model exists, so that will be asked. Let's go to some of the old assignment questions then. So old assignment questions are actually the last year these questions were asked about this model. So I have tried to take all the question of the assignment for week 5 in the last year, and I have placed them as and when we have covered that particular portion. So pointing on WIMP interface is same as 1D pointing behavior modeled by the classical Fitts law. Is that true or false? You can write your answer in the chat box. Okay. Jyoti, you want to answer this question? So Dr. Roy, I am sorry to say, but it is answer is false. And now I will give a minute for you to think about it. Why would it be false but not true? Or if you want to think that it is true, can you unmute and say why did you think it was true?
Madam, because uh, window, I think icon, then mouse
Menu,
pointer, correct?
menu
Na?
and pointers.
Ah. So this is looks to be 1D. Mm, uh, that's what I feel, because it is on the surface. Okay, uh, it is not XYZ plane. So that's what my thinking is.
So agree that it is not on the XYZ plane. Definitely, it's not a 3D model. But is it
Hmm.
1D though? Are we talking also about the windows placement? Windows could be placed anywhere, right, on the screen. So we are essentially talking about the two dimensions, vertical as well as X and Y, on our screen.
Okay.
That's the reason why we need a 2D model pointing behavior instead of only
Okay.
1D pointing behavior.
Okay.
Yeah.
Okay.
Next one, in bivariate pointing model. Huh. This is basically a recollection kind of question, a recall level question. Very good, correct. It is amplitude pointing. In the bivariate pointing model, T is the dash in the task acquisition. Response time. No, actually, it's the movement time. Why not response time? I have an answer to that. Actually, the word we use in last week we learnt another law, Hick-Hammond's law. It uses not response time, but it calls it reaction time. Reaction time is the time you take when you are given a few choices to make, and you have to select one of these choices. So that is the reaction time. But today we are talking about the task acquisition, so we already know which target we want to acquire. So we don't have to make a choice which target we want to acquire. We just have to make a movement of the pointer from one place to another. That's why it is the movement time. Okay, another question. So I see that a lot of questions have been asked regarding the 2D and 3D versions of this Fitts law. So I think that is going to be an important topic. Well done. C is the correct answer. It's a combination of both amplitude pointing and direction pointing, because we are talking about the two-dimensional view. That's why. Very well. So now next part we are going to talk about the constraint navigation or tracing boundary. So far, if you have any question, or if any time in between, if you have any question you want me to go over something again, we can do that. We get the time has been orchestrated in such a manner that the pace would be as per your comfort. Okay, so constraint navigation, it basically is like tracing a boundary, not just moving this pointer. So you can see my cursor moving right on the screen. So right now I'm just moving this pointer, but tracing boundary would be like drawing a kind of square on the screen, so in which you are actually pressing the pointer as well as dragging it. So that is the tracing boundary kind of movement. Okay. Constrained navigational tasks are the tasks in which we are constrained to move our hand or finger or mouse pointer through a tunnel like pathway, kind of a pathway having a fixed width. So, this pathway would have a fixed width, and it would be known to us, previously known to us. So, for this constrained navigation, something like a tracing boundary, we have this steering law. So, this steering law also gives us or also models the movement time, just like the Fitts law. It models the movement time in constraint steering. Only difference is in Fitts law, you were moving the pointer and then you were clicking someplace. In steering law, the clicking and movement are both happening together. So it was suggested as an extension of Fitts law, this steering law, by the same Zai and Ackert, so who gave the 2D and 3D versions of the Fitts law. So this, what does this steering law tell us? That initially we had, if you recollect the previous formula, initially here we had a capital D giving the distance of the target. Now what it's saying is, imagine tracing the entire line while the pointer is being pressed. So you have to imagine very thin segments of the width of the distance at a distance ds attached all together in a packed manner. So along throughout the distance there are ds these tiny sections. This ds will be there. So the all the ds, their integral would give us the ids. Okay, so all these small segment together will give us the ids. I think I should have drawn a figure over here instead of, yeah. I'll just refer to this one first. Here. So here we saw, right, initially this was the previous first position, initial position, this was the target, and over here we were only traversing this path and then clicking over here. Now we are imagining that every moment we have clicked and then reached over here. So that's why for every click we have calculated the id. So this id would be replaced by so within this id formula we replace the d by the small d, this very tiny segment, and then we integrate those segment along the entire distance. So S is basically the number of segments, infinite number of segments that constitute the length of the or the distance of the tunnel. And since it is infinite, there is also this important thing to remember, that the width of the target, the place where we want to click, that is again much more larger than this small ds. So that is why we can also simplify this. We can take the logarithm outside, and this becomes the new formula. And again, to model this formula, movement time, this was the index of difficulty, and we saw that index of difficulty is proportional to the movement time in through this equation. So that becomes the model of our steering law. Okay, why is steering law given? What it adds more towards the Fitts law, it tells us about the constrained navigation or constrained tracing. Okay, so here the a and b empirically found values are this. Basically nobody is going to ask you these values. Just remember that this steering law has been derived from the Fitts law. And why has it been derived? Because Fitts law only talks about movement and then clicking. Steering law talks about pointer being clicked throughout and the tracing being done. It talks about the constrained navigation. Constrained navigation is a task in which the movement is happening of a pointer within a fixed tunnel length. So the note on steering law. So for the steering task on a trajectory having constant tunnel width. So here we saw ws is within the integral, right? So for this constant tunnel width, so suppose there are multiple tunnels and each tunnel has the same tunnel width. The index of difficulty is not a logarithmic term. term, but it becomes a simple ratio d by w. So then in that case, movement time becomes a plus b d by w. So d is the total distance to be covered within each tunnel, and w is the width. So let me do one thing. What I can do is, if I think we have some time, we can go back to this tunnel. What do we mean by this tunnel? Okay, so that I think within the lecture sir has covered it. I didn't cover it because I thought maybe we can go ahead. So the difficulty for the entire task is the addition of individual difficulty indices in that case. So basically there say, yeah, let me just draw this. Okay, so now consider me drawing this shape of this square. Okay, so while I drew this square, my action motion was like this. My movement of action, it happened like this, right? This was my action that I performed, and throughout this arrow, tracing this arrow, I have kept my pointer pointer dragging, continuously dragging. Okay, so to the tunnel would mean this chunk, this chunk along this line, along this sorry, not this one. A tunnel would mean a fixed length across this, a box of fixed length across this arrow that I trace. Okay, that is the tunnel. So this is the tunnel. So this is the tunnel. This is the direction in which I am moving, and this tunnel would have a width. Now suppose I were to draw this square and then another square next to it. So I would have done one more action after this. So what the Fitts law says, that suppose it was the same amount of same square that I was drawing. If the action is constant, remaining constant, then we can simply add the two arrows. So two arrows as in the difficulty for the two arrows. So this is basically an addition of the difficulty in case it is the same task being performed, or the width is constant. Okay, so that is one of the constrained actions that was tracing or drawing something, drawing a boundary action. Okay, so this is the steering law that gave us the difficulty and the movement time for drawing a boundary of something. Next is the constraint navigation menu selection. I think if I have confused you, you can unmute and speak. Oh, constant A and B, how they are calculated. Okay. So this A and B are basically calculated through. So last week we have done this. What we do is we perform one task for multiple users, like thousands of users will perform one task multiple times. We take the average of each one's multiple times, then we take the average of everyone who has performed, average of those averages, and we get this model of what could be the perfect fit for this A and B. So basically we do the fitting like it could be done by linear fit, or it could be done by regression fit. All these ML algorithm is used to calculate the A and B values for thousands of trials. Remember, this is happening for multiple number of trials, so there is a lot of training data to find out these values of A and B. Okay, definitely there will be difference between the novice and experts for this tunnel steering law. Oh, okay, okay. You are talking about multiple users. Yes, definitely. So what happens is when we take the thousands of users data, there are sometimes they would classify the novice and experts. So thousands of novices and thousands of experts, like that. But for the movement pointing action, usually there is not consideration of the novice and expert like category. This novice and expert category calculation happens for mainly for typing tasks, because usually the typing speeds of users, novice users and expert users have a lot of large difference. But the screen tracing or pointing duration is kind of not that different for the novice and expert. That's why when we talk about this Fitts law, steering law, we don't have a lot of different A, B values. For model doesn't depend upon novice or expert. But when it comes to typing tasks or entering key, then at that time this novice and expert would come into the picture. In the same way, right now we are talking only about the computer screens, right? So if you imagine a VR headset wearing person performing some task, at that time there will be difference between how the novice has gaze pattern and how much time do they take, and how the expert will have, because these are newly introduced devices to people, right? So there is a difference between the novice and expert performance. But since screens have been there in an integral part of our life for approximately 10 years now, at least 10 years now, in the modern era of computing, starting from 2011 onwards, so that's the reason why now it is an assumption that novices and experts have a similar um, uh, pointing task time. So I believe that in the physical motor motor there were seven operators, and out of these seven operators, five operators are this physical motor category, and first one is related to the typing, while these all these movement of the pointer, clicking of the pointer, are all the operators which belong to this category, where experts novices don't have that much of difference. If I will give you a recollection of that slide, just a moment. Yes, so these are the physical operators. uh, I hope you're able to see that screen. Just a minute, I'll check. Yes. So K operator represents the key press type, which is related to typing. B is the mouse button press, that is clicking. P is pointing, that is moving the pointer from point to a target. H is homing task. Usually now we have discarded this. Sorry, now this the drawing line is not used. Homing task is switching between a keyboard and a mouse pointer or a touchpad. Different device, input device, rather than homing task is about switching the homing input device. M was the thinking or decision making task, and R was the system response time. We are today talking about these five physical operators, and within those, these are the for novice, intermediate, and expert. And for others, if you see, there is only one timing given, because there is not much difference. Okay, so that's where I am referring to. Okay. So now we are back to this steering law. So remember that steering law is still an extension of this Fitts law. We talked about this target acquisition in 2D, 3D. Now we are about target acquisition, but while the tracing action is done, I will again once more talk about this example. There is some flaw in my example, okay? This is not a constrained thing, it is not completing a boundary. So, this action was not completing a boundary. I was drawing a boundary like this with this square. So drawing a boundary is this, drawing this square. My movement was happening of my pointer in this arrow direction, and that's why these two lines are representing the tunnel. Next, is there any other question on the chat? I'll just go through it. Okay, tunnel means 2D. Yes, there are two dimensions. But the interesting thing is, we are not considering this vertical direction. So tunnel is model, in the model we only consider it as the one dimensional Fitts law. We go on fitting it, and then we add the number of tunnels that it took to draw a boundary. So here, when we drew the arrow, it was so when I trace the arrow, it is pretty simplistic, one single line to complete the boundary, right? But it could be a freehand drawing of the boundary. So in that case, there will be multiple tunnels that you can fit around this my action of my pointer, trace of my pointer. So what we do is we add all the ID, index of difficulties for each pointer. Yes, it is one dimensional. Yes. So, okay. Yeah. Difficulty for the entire task is given by the addition. Now talking about this menu selection, so I will again give you a demonstration first. So initially on this screen, if I want to have some create something like I want to download this entire PowerPoint presentation, so we have multiple steps to do that. So first I want to take my pointer to this file point. I want to click on this, then only the menu will appear. After clicking, then on the menu I have to make a choice. So remember, here I am presented with choices. So here my time gets taken, and that time is reaction time again. Now I want to select one of these. When I hover on this particular element, then only I see another menu within that element, and then there are multiple options for that. Again I have to make a choice. So again a reaction time appears over here, right? So that's why it is a menu selection is a little bit different than the steering law tracing boundary thing. V and H. V and H. I didn't understand V and H. Oh, okay. Yeah, right. So even though there are vertical and horizontal movements, the important key point is at the beginning. When I can see the screen, I don't have the reaction time or the choices in picture. I just know that file menu will give me some place to start off with downloading. So that's why menu selection, even though it is again a constrained navigation action, it is different from the tracing thing. So tracing a boundary was one type of constrained navigation. There are multiple types of constrained navigation. We are studying the first one was this tracing boundary, and the second one is the menu selection. You are correct. We have vertical and horizontal pointing tasks. So the idea is the same. There is vertical movements that happen because of the Fitts law, but the horizontal movements are happening because with the steering law tasks. So it is a combination of this Fitts law plus steering law. So yeah, so this I have initially added. So based on your understanding of this vertical horizontal movement, if you can answer this question. In the basic menu selection model, difficulty for the entire task is dash of the individual difficulty indices. Would it be addition or multiplication? Hmm. Okay. So basically, the Fitts law, vertical movements Fitts law, because now I have clicked on file and my pointer is on file. I have made the decision to go to the download, so I have to trace this vertical movement. So this, there is a pointer movement time. So this movement जहाँ पे भी आ जाता है, wherever this movement word comes, you get the idea that it is about the Fitts law, because it models the movement or the motion movement time. Then when I click steering, क्यों आता है horizontal? Why is horizontal the steering law? Because I have to maintain this down my cursor on the download thing only. If I move it here or here, then the menu will disappear. That's why this comes under the horizontal movement, will come under the steering law. Steering law again is an extension of the Fitts law itself. So it still talks about this pointer movement, but it is a pointer movement in the constrained area. So if I go here or here, the menu is going to disappear. That's why I have my constrained area of this download bar in which I can move. That's why it's a constraint task. So I will apply the steering law for the horizontal movement and only the Fitts law for vertical movement. Is the answer okay? Clearer? Shall I go ahead? If you want me to explain again, I can do that. Equation, it has 3 parameters for 3D movement. In Fitts law equation, it has 3 parameters for 3D movement, but for the single dimension or two-dimensional motion, it is only 1 or 2 parameters. Here we are considering for vertical movements only, so that's why it is a one-dimensional Fitts law. One-dimensional Fitts law itself will have parameters. So so the parameters like this A, B, W, D, all those will be there in the law. Okay. Next. Yeah, so here it is basically the addition of individual difficulty indices of the times you have to do the more vertical tracing, then times you have to do the horizontal tracing, vertical and horizontal. All those actions you have to calculate for each. Yes. So, and then add all the difficulty. So now here is an activity. You can share which is your way of typing, whether you type in this way or this type in this way. 1V and 3H. 1V and 3H. Okay, correct. Okay, B. Jyoti has been silent. Jyoti, if you want to also interact, it would be good if you try to answer, so that answering wrong is also fine, because we are here to clarify our doubts and solve the problems together. So usually I also prefer to type with both my thumbs, so this is B also for me. But in the earlier days of phone, I used to prefer the one finger typing, finger touch typing, like A. Now, even today, I mean, on the touch screen phones, I have seen multiple people who are newly using the phone. They prefer to type in the one finger touch way, and there are some tasks like where you don't want to type a long text, where you can still use the one finger touch type of activity. Okay, so this was basically just a segue into our next modeling. So now we want to model how mobile typing is done for the people. So the aim is for us to make our user layout for the typing activity. We want the aim is to make the text entry rate maximized, so that typing will be faster, in simpler words. So words per minute or characters per second we want to increase. So there are two types of typing. The first one we have seen is single hand or finger touch typing, and the second one is two thumb typing. To model the single hand or finger touch typing, we have Fitts digraph model, and for to model the two thumb typing, we have two thumb typing model. So now we will first go towards this single hand or finger touch typing, and we will talk about the Fitts digraph model. So my first question, since I am not a native English speaker, which one is faster? Yeah, so it depends what is the activity. So you can't say that something is faster just because you're using the thumbs, two thumbs. uh, it depends on the task that you are going to perform. For the single task, if you perform it using single touch pointer and using the two thumb typing for pointer, it could be a task that doesn't even require two thumb pointing, just for instance, when I am drawing my, say, pattern to open my screen, I don't need to use two thumbs. So depending upon the activity or the task that you want to perform on your phone, your requirement of the mobile typing action will also change. So it isn't the choice between one finger or two thumb that makes the. Okay, you are asking about typing. Again, I would say that it depends on how much you want to type. So if you want to type more text, it's actually preferable to type with two thumb or typing, because you are essentially using both your two of your, you are using your dexterosity to type. If you go on typing with single finger, you will take longer. That is definitely true. So I'll go ahead now. Only for the typing task, if the task is the same, entering text, if the task is entering only one single letter of text, then again it is debatable whether single touch or two thumb will make a change or not. Single y or n typing, like that. So you may not, it may not make difference. Multiple letters in a word you have to type, then it will make a difference. So now next, another activity. Have you used any of the following letter combinations frequently while typing some words? So there are pairs of letters shown onto you. Yeah, so yes, so in English language, there are, these are the kind of combinations of consonants and vowels which we use frequently. These are known as digraphs. So digraphs form a unique syllable in English language, which we have a lot of frequency of these digraphs appearing while we type a word. So that's why in the typing activity we consider with how much probability are we going to type the digraphs. That's why that inspires the idea, or that is the idea behind the Fitts digraph model. Okay. E letter has more. Yes, so it depends. Some research has been conducted, and it was found that these are interesting findings. So E has been the letter, one of the vowels that is most used is E, and There is again another thing that in a lot of harsh words, R is the R or K are the letters that are most frequently used if somebody has to write a lot of harsh words. So such researches are also part of this computing for user understanding the users. But now we are talking not only about typing one letter, that is important thing. We are talking about this digraph, two or more letters. So while we are typing, interestingly, we have what we are doing on the touch screen is that even while we type with two thumbs, each of our thumb will travel from one letter to another. Subconsciously we are thinking about this traveling of our this movement of our fingers. So the model of this user is now happening for mobile typing. It is happening at that micro level. We are going to model based on these digraph probability. So digraph is two letters that are combined to make a single sound in written or spoken English, like th, the, sh, like that. And we consider the digraph probability. How much probable is this going to be for typing, while typing, and we model the average movement time to between the any two keys in the layout. Okay, so that's what we are going to do with fits digraph model. Consider this fits digraph model, it was for the single finger touch type. What was the correct answer for? Oh, no, there was no correct answer. I just had this activity because we want to know what the digraph means, right? It was my initial confusion. I didn't have background of what is a digraph, so that's why I kept this activity, so that we recognize that there are multiple such letters, the combination of these letters that we use, which are called as digraph. So there is no this wasn't an old assignment question. I'll yeah, this is just an activity, it's not an old assignment question. Okay. Next one. So we tried, the aim is to calculate the average movement time and model it to while typing any two keys in the layout. Fits digraph model is for the single finger touch option. Okay, so for typing performance single finger touch, we take the fits digraph model. The aim is to again recollect that it was to maximize the text entry rate. For that we want to improve the typing performance of the user, and to achieve that we are trying to minimize the time for them to locate and move finger across the different letters that they want to type next. Finger as in, remember, this is for single finger touch operation. And then we will see the two thumbs touch operation, what happens for the two thumb touch operation. For single finger touch operations, we have the actions that we do are locate. So location of the next key to press, we have to figure it out. Consider all the keys presented on the keyboard layout, virtual keyboard. VK is virtual keyboard as a choice. So to select one of those, it will be the reaction time, and that can be modeled with the Hickman's law as we have previously studied. And the move operation, it happens with move as in, first we locate where is the next key I want to press, and then I move our pointer. So moving will happen with the Fitts law. So that's why we are modeling this typing performance in terms of this Hickman's law, a combination of Hickman's law and the Fitts law. So you might have these questions in the exam, like for if you were to do the menu operation, then which law combinations would you require, and if you were to do this single finger touch operation for typing, mobile typing, what kind of laws law combinations do you need to use? So this kind of questions might come in the NPTEL exam with options. So there are always usually there are options for the NPTEL exams. Now this for locating, we have to model the reaction time, and the reaction time equation is this. For the virtual keyboard there is A and B, and N is the number of keys presented on the keyboard. N is log 2 to log of n to the base 2, that has been found because there are n keys which have I'm sorry, the same typing time. So n is the number of keys presented in front. All the time keyboard layout gets changed for security purpose. What is your comments on that? Yes, so virtual keyboards in which the for security purpose they change it. The intention is to give more time, because they are not trying to make it easier for the user, essentially make it difficult for the user, because they want to detect that a human person is trying to operate this and an authentic person is trying to operate this keyboard. So the intention here is uh, quite the opposite of what we are trying to do to make it user centric. So while we try to make it user centric, we try to make the users typing and task execution very fast. But when we are trying to differentiate a human from a robot or a uh, malicious threat, then in that case we try to make it with the intention is to try and understand whether a human is actually typing it or not. So the intention is there in the where the for security reason virtual keyboard keeps shifting the layout, is that to delay the reaction time. So they are also trying to do this, they are trying to reduce the typing performance, because for a normal human being it is supposed to delay the typing performance. If a robot is operating the same, they will be able to select the same key very fast, or select the same key as in enter the right thing very fast, much faster than the human. So that's why they can differentiate that it is not a malicious software that is trying to hack into the account. So that is the principle for this changing layout virtual keyboards. I think that what I learned recently was that when we enter the captcha in Google, like there are some captcha up captcha or something that appears, right? We have to select some tiles in which we can see parts of the bike or parts of the crosswalk, that we have to make selection. And initially I used to get worried, what if I miss some place, there is very tiny part of the crosswalk, should I click that tile also or should I leave it? So in such cases of captcha I found out after reading up about it, that it is not your accuracy that they are testing, it is the movement of the pointer that you do to select those tiles, and the time that you invest in reaction to those tile choices. That same thing, like this fits diagram model that is measuring the locate and move per times. So that time they are measuring and finding out that it is a human, because it is taking time to make this decision. It's not a robot, so it would have been easier for a robot. So so the captcha actually doesn't validate the accuracy, it validates your actions, movement and tracing and the clicks. So that's an interesting time. Thank you for this wonderful question. We'll move ahead now. So for the locate, we measure the reaction time. Reaction time is modeled based on the n number of keys as choices. We use the Hick-Hyman's law and we model it like this. For the movement action, we use for Fitts law and we model it like this. Here, I, J are the ith key that I have pressed while typing and jth key. So I and J are not the keys, ith key and so it could be first key, second key, any key. So so while typing we type multiple, we are going to press multiple keys. So the ith key and the jth key is what is being modeled. So this is for Fitts digraph model. Based on this Fitts digraph model, basically you then measure the locate and move. Addition of all those will give you the total movement time. Okay. Typing performance is dash proportional to the time taken by tasks locate and movement. Inversely. Correct. So the time taken is higher, the typing performance would be slow. Very good. Next, so this is basically the same thing. We have spoken up to this. Probability based. So where does probability come into the picture? Probability actually solves the problem for us. Okay, why? Because for an expert, this reaction time might be very little, because you are an expert, you have been using this QWERTY layout multiple times, or sorry, whichever layout you use, you have been using it multiple times. So for an expert, the reaction time of the location of multiple keys, that is negligible. So for the novice, reaction time of the location also is considered. For the expert, it is not considered. Now this mt is the movement time mean. Movement time was given by uh, this initial equation, this one ij. Okay, so now what they are saying is, since all the keys are going to have the same width, and there is a probability based on these digraphs, right? We initially saw some of the digraphs. So these digraphs are going to happen much more probably than the other letters separately in the word. So that's why the probability comes into this picture, in which we can use probability to say that probability a digraph is being typed Pij into mt, moment time of ij. So we sum up all these and we get the this equation. The previously we have shown this equation. It came from the probability. Okay. Now digraph probability can be found from a dash of text for a language. Yes. So it's basically a question based on recollection of your lecture. Uh, Actually, I don't think that there is a. I have covered this question. So corpus of text of the language. Corpus as in. So in the lecture, sir covers the British national corpus as the corpus of consideration. This corpus will give us the probability for each digraph. So this digraph probability is mentioned in each of the language text corpuses. In Fitts digraph model, dash is used to model performance for the locate task. Locate happens first. Yes, correct. It is Hickman's law. You model the reaction time in the locate action, and then there is move option action where you model the Fitts law. Correct. Now the two thumb typing model. Similar, it is similar. Only thing is we talk in terms of which thumb we use. You will see that the structure of this model is also similar to the previous one. Like there will be some constant, something, some typing plus some constant into t min. So what is the t1? T1 is the time to type the first character in the two thumb typing model. Type the first character is given by these equations. You don't need to remember the equations. What you need to remember is that this t fits is the time to perform a fits law task, that is locate a target. Source is the space key and target is the first key, first character. Okay, so from space you are moving somewhere. So why is this space key taken as a reference? Because it sits in the middle in the QWERTY layout. So that's why they take the space key as the center. And they also say that usually when we begin typing, we begin with a space key, or after a full stop we have to give the full space key and then we start typing. So in that sense, space key is taken as the reference, and it is said that the first character will be typed after the space. So that's why your fingers will lie around the space key. Is it true for left-handed person or right-handed person, writing person? Okay, so in the lecture it does not say for right-handed person or left-handed person. It does not say in the book as well. So what I know of is we are modeling for a two thumb typing person, uh, where the right hand is taken as the prominent hand. Because why I am guessing this, so this is not explicitly said in the video lectures or the book. Why I am guessing this is because it says that over here you see there is 0.70 and 0.30. This comes from this first letter, first space to K1, and it was said that 70% of the times after a space key you begin typing with the right thumb. Sorry, it is based on the words that exist. I will have to check this. I think I will have to check, and I will do one thing. After I post on the YouTube, I will comment with the answer where this 70 and 30 comes from. I think I have some confusion, but it is not based on the right hand preference or left hand preference. Okay, so whether a person is lefty or righty, it was not yeah, so it is not based on that. I think it is more based on the user behavior, either on the user behavior irrespective of their right handedness or left handedness, or it is based on the words that appear. So why right hand and left thumb we are talking about is, roughly you divide the QWERTY keyboard in half, but it is not the straight half. It is kind of a slanting half, inclined to cover more keys in the right area. So that's why they say that you first usually prefer to start with right hand side. 70% of the population prefers to start with the right side. So I just have to get a clarification whether the population prefers the 70% right hand side, or the words are such that you have to enter the right hand side first. Okay, so I will get back with this question in the comment section where I post the YouTube on YouTube. Okay, so that's why this 7.70 and this 0.30 has been placed over there. So from the space key, you first, usually the first letter is typed with the right hand thumb by 70% of the population, and that's why they have multiplied it with 70. So it is the first key. The T fits is about the action of the movement. And then T min is the minimum time between text entries with alternative thumbs. So it is with the uh, within the first, for to type the first letter you are going to uh, use the T fits, and then T min is the minimum time between the text entries within alternative thumbs. So when you are typing an entry where you ended something with the right hand side and you are to move now, switch to the next hand. So this switching action is represented by this T min. Okay, now the question is for you. Another activity, it is not a assignment question. Guess which combination, typing for which combination would take longer for time for you. Suppose you are typing KB, then you are typing AZ, and then you are typing QN. Which one would take longer time for you? It's okay to give a wrong answer. Perfect answer. So QN would take the longest. Do you have a reason for it, Dr. Roy? Why you are on mute if you are speaking? Why it would take longer to type QN than the other two combinations? Yes, so while you check the keyboard layout, you must have checked that Q and N are placed in a different placed afar. Similarly, to type Q and N, you will usually use two different thumbs rather than typing them with one thumb or one finger or one thumb, same thumb. In the AZ combination, it is the fastest because you are typing with the single thumb and both the keys are placed at a small distance. While typing KB, I still use the right hand side thumb, but the distance between them is farther than the AZ combination. Look at your keyboard and you can observe that. And then to type the QN, you have to first you have to type Q and with one thumb, and then you have to switch the thumb to go to N, and the distance is again from the space bar. The distance of these two keys is again farther. So that is the reason Q1 would take longer time. So here we talked about two things: same thumb and using the opposite thumb to type the letters. Initially we have done this T1. T1 was for switching of to type the first character. So this T1 gets in importance because first character we begin from the space bar. And now we talk about this TN, so nth character. Here again, this, if it is the first character, sorry, I will first talk about this first, same thumb thing. So if you can type a word within the same thumb range, within the vowels and consonants that fall in the same thumb range, the time taken would be time, Tn is modeled as Tn plus Tn minus 1 plus T fits. So going from the previously typed letter to the next letter, so that time is given by T fits. Kn minus 1 to Kn is the next letter, going from one letter to another. So this is the time taken by given by Fitts law, moving action from one letter to another. And Tn minus 1 is to type that last letter. So that typing time is T. So this is the total if you are typing with the same thumb. But when you are typing with the two different thumbs, a word that consists of the entire layout, so at that time there are two times you will consider. Either you will consider Tn minus 1 plus Tmin. So Tmin is switching between the hands, and Tn minus 1 is the last hand that you have done, that you have performed. And or you will talk about this again, this last entered time, uh, last time you have used the same thumb, and then you switch the thumb. So this was for the same thumb. This is for the switching of the thumb after typing k letters in the same area. Okay, so this is a little bit complicated. I think to just to simplify things, we need an example. Okay, we have typed this kb in the same region, and then we have typed this az in the same region in the initial example or the activity that we did. Okay, so when we did the az and kb, both were lying in the same thumb regions. So for kb it was right hand side thumb, and for az it was left hand side thumb. So that's why the time taken to type them can be given with this. So kb, in this k and b become the n minus 1th and the nth letters. Similarly, a becomes this and z becomes this. So ath letter, typing the a letter and typing the z letter, that ends, that question ends over here. Next is the typing q and n. So typing q and n, these only two letters are there. In that case, I have n minus 1, tn minus 1. So I type q. So time taken to type that q, and then tmin, that is switching the hand and then typing the next letter. So that is the my option for first thing, where only switching is happening while typing. Okay, now suppose between the switching, if I were to type this word send, if I want to type this word send, or if I want to type this letter type this word seal, seal. Yes, so I want to type this letter seal. Okay, in this case I have S, E, A and L, out of which S, E and A are three letters that fall in the same left hand side zone, and then I want to use the opposite thumb, that is for the typing L. So that's why they do the Fitts law only for this switching action, and then Tn minus k, that is the time taken to type SEA. There we do not consider the T minimum because switching hasn't happened. Over there Tn minus k is the kth time at which you have to shift the key, you are using the same thumb. So there are three letters while which we were typing with the same thumb. So in the Tn minus k plus T Fitts, if you look at the top, same thumb thing is repeated over here. For these k terms, for these k letters, I mean 3 letters, you will apply the same thumb model and then consider typing the nth letter. So that's the only difference. Why we have to take the maximum of both these? Because this is what happened when we switch the hands. This is what happens when we were using the same letters. So that's why either the time taken to type will be more consumed while switching, or it will be more consumed while typing on the same side or using the same thumb. That's why you have to consider the time that was taken maximum during this action. This is nothing but same as this top thing, this second part, and this is for the switching action. So we are taking the maximum because we are only considering the time that is taken to either switch, that took longer time if that took longer time, or we are considering the time to type the things that were on the same side. So in case of this word seal, because there are three letters on the same side, S, E and L, S, E and A, probably it will take longer to type S, E and A even though they are on the same thumb side than typing the L, which is on the other side. Switching time is lower than the same thumb side time. So that's why in this case, to type this letter word seal, you will take the maximum as the SEA combination. SEA combination typing takes the maximum time, so that time will get considered. Yeah. So exactly because of that, there are word combinations that could have the other way around also. So some words in which you will need to switch thumbs multiple times would be there. So in that case, this t minus 1 plus t min would be higher. This first component would be higher in that case if there are multiple switches than the same letter typing. So we are considering the time that was taken larger because that is useful for modeling, right? The larger time taking gives me the understanding that this is the time consuming thing. Yeah. Okay. I am sorry to confuse you initially and then take you through this journey of figuring it out. Okay. I hope that it is clearer a little bit. I would go next now. Yes. So this is just giving the times for the constants of the model. Again, these model constants are done with fitting of the entire data that has been collected. This was T1 and then this is Tn. So we consider both the timings in case of two thumb typing model. There would be any question about the constant, but there could be a question about what is Tmin, what does Tmin stand for, what does Tfit stand for, what is the Ki and Kj, like that. So basically K are the number of letters present on the same thumb side in both these cases. Okay, I will move ahead now. So we will take a 5 minutes break. Okay, we still have a very loaded model to go. K is the number of letters. Yes, K is the number of letters that lie on the same side while you are switching between the you are typing a word that requires you to switch. Even there are words like seal rows where there are some K number of letters which are on the same side. Break activity. So within this break activity, kindly list down the frequent actions you perform on your device like a laptop or mobile interface, touchpad. I'll just take a, we will, we can take a shorter break also. We'll just meet in 2 minutes. I'll take a break. I'll have some water. Thank you for sticking around. We just have one more last, model to go now and cover the questions related to it. So the symbols and special characters, we don't have these covered in this scope of the lecture. So We are talking about typing the regular words only by this with this in the scope of these lectures. If I think I will note this down. If in case I find it somewhere in the book, I can post it on the discussion forum of the NPTEL group. But I don't think it has. They mentioned it. Hello Somanji. So first of all, I'm back with the answer for previous question. Right-handed persons or left-handed persons. So it doesn't say that it is for the right-handed person, or preference of the hand is not the question over here. I will read from the book. This is the book from by Samit Bhattacharya sir. It is the human computer interaction for user-centric computing for design. So it says that this thumb movement can be modeled with the Fitts law. McKinsey and Sokorev found out that the right thumb is likely to be used to select the space key before start of the word in 70% of all text entry tasks in English. It doesn't say whether it is by a right-handed person or a left-handed person. It is for page number is 147. So it is based on all text entry tasks in English language. If the first character falls in the left half, these weightages get reversed. They say. Other quantity, okay. So it doesn't say based on the person's preference of location. Regarding your question about the university, thank you for the question, but I'm not an expert to give an opinion about this. I would encourage you to write to Professor Samit Bhattacharya ji for um, on the forum itself. There is a discussion forum on the website on the NPTEL or Swayam platform, in which you can post your query. It will be wonderful to hear what would be uh, required for your background, because he has a lot of experience in that area, so he would be a better person to guide you. Thank you for your questions. So are there any answers for the in break activity? List down the frequent actions that you performed on your device, laptop or mobile touchpad. So why do you use the touchpad for? Navigation, right? By navigation you mean the movement, pointing, yeah, selection, right? So you perform the tapping action. Anything else that comes to mind? There is something like this that we do on the screen. So there's zooming action, or there is a scrolling action that we perform, right? So the most common three fundamental operations are there. One is tapping, then single finger scroll, and then multi-touch gestures. The one that moving action you told, navigation action and selection, navigation action, that we have seen so far. It is the same thing, using the Fitts law of uh, for selection thing. Uh, so that navigation has been covered. Now we are talking about these three fundamental operations on the touch screen, that is tapping, single finger scroll, and multi-touch gestures like zooming in, zooming out. It could be two finger scroll mechanisms are there in some touchpads. So such multiple gestures can be used with the touchpad. So in this lecture or in this coursework we have in laptop or mobile phone anywhere. So touchpad is there on your laptop screen as well. So sorry, laptop touchpad is also provided, so we considering that also. So we are considering that also, yeah. I think for the purpose of this yes, so these touch actions are both for laptop as well as mobile screens. Next, so we are going to model only the tap actions for this for the scope of our content. This tap action is again a type of target acquisition, but here there is a big difference. We cannot apply the Fitts law directly, and there are reasons for it. Fitts law had three main assumptions, key assumptions. One is it should be rapid, it should be aimed, and the third one is it should be error free. So rapid means Fitts law can be applied only for the fast movements. It is not for a slow movement task. Second is second assumption was that Fitts law is should be aimed. The target should be known to the user, okay, where I want to go next. And third thing is the error free rate. So Fitts law assumes that the user performing something has error free operation. When multiple trials were conducted based on the clicking behavior of users given a target, it was found that 4% of the users 4%, if the users are missing the target by 4%, it is okay to ignore that error. But if they end up missing the target for more than 4%, what usually is suggested as a remedy is increase the width and height of the target, so that the area at which they will click would be in the right region. That was what we covered in the last lecture in the classical models, last week's content. This week we will talk about why it is not appropriate to apply this law directly to the touch based operations, because we are performing these touch based operations mostly because with our finger pointing. So the target width is much less than the pointer dimension. So there is a finger width height that we need to consider, whereas the touching area surface is also provided very small, and the target is also very small. Attention factor, no, so attention factor is another term altogether. Attention factor doesn't talk at all about the dynamic thing. It talks about the static thing that is presented to the user. I'm not talking about the attention factor. I'm talking about the same Fitts law that we had earlier studied. This target acquisition, difficulty index, all those things that we have been talking so far. Attention factor was much before that in the last lecture. If time permits, I will go over it. So the reason here is that in terms of the touch actions, our finger might be nobody can call this finger as fat actually, but if you consider the very micro and nano particles as the points on your pixels on your screen, all those things. In that dimensional way, the finger it is recognized as the fat finger problem. So because of that, chances of error are much higher than 4%. So that's why there is a modification to this Fitts law. It is modeling finger touch with Fitts law, but specifically for this finger touch. So same researcher has been, you might have observed this, the same researcher has been working in this modification of Fitts law over a lot of years. So what is this Fitts law modification? Here instead of the W we have this. The sigma is the standard deviation of the hits around the center of the target. I think I have jumped to the most simplified version of the formula, because derivation is not so complex, but it is based on assumptions. So that's why I have jumped to this formula. This is the standard deviation of hits that is correctly pointing at the target around the center of the target. So this is again another distance. So it is given in terms of the distance up to which the deviation might occur. So this IDE is the is given by this law. And here it is important to know that when we talk about the finger touching action, there are two types of this standard deviation. One is relative and another is absolute. So relative standard deviation occurs because of the finger movement being actually wrong. So even though you want to click on something, you might actually miss it because you have missed the you have not gotten the frame of reference. For example, if I intend to go from this I to this D, there is a chance, even though I want to go to this D, I might end up somewhere here. There is a chance. Okay, so that is the relative error. Whereas there is an absolute error, which is because of my finger width. So this is the absolute error. That is, say my finger width itself cannot do a precision action. So that's why I am relying somewhere here. So that is the reason it is the sigma we have to consider relative as well as absolute. We have to replace this sigma with the sigma r, which is relative, which is given by the original standard deviation square minus the absolute standard deviation square. How this formula is derived is not in the scope of my problem solving session, but it is there in the lecture. The moment times prediction model for this target acquisition. So this is basically the ID, that is index of the difficulty. Same way we have learned that it is proportionate. So the same structure of Fitts law is here applied everywhere. Only thing is here we have replaced the sigma with sigma r. To model this, we need to model all these four things: A, B, sigma and sigma A. So sigma A is also absolute, sigma is also absolute, these sigma A and sigma are also modeled, and that gives the movement time for any user. So to create the model empirically, we have to identify these four parameters. How this empirical identification is done is explained in detail in the lecture towards the end of the lecture. I think after the 3/4 of the lecture or last lecture of this Fitts law, you will see there is an explanation of how these values are calculated. The basic fundamental process is the same, of conducting multiple trials and acquiring for each and then averaging them out. only the assignment questions regarding this covered just these much problems, so these many this much content, so I have concentrated explanation only on these. A correct. Very good. Next question. Sigma A, but then there was A and B as well in the formula here. A, B, you have to model all four parameters. Sigma A and B. So that's why the answer is 4. So this is it's called for end of week 5. I am just going to check if I find the uh, attention factor thing. I think we will be out of time now, otherwise. Okay, so we have 5 more minutes. I'll just try to find it out. Yes. What about D? Okay, so D is not modeled. D is, what is a model? Model is, you have certain elements will be there which is user specific. The key thing is, we are trying to predict for the next user that comes up, how can I find out the moving time? So for this next user, there is going to be something specific, some specific value. D is the specific value that we will observe for this next user, for which we want to predict. But all these 4 factors, A, B, sigma A, are the factors that can be empirically found out irrespective of the user, because we have so much of training data of the users. So computation is taking care of establishing a fit in which will be some linear equation in which, in multiple 1 or 2 variables, out of this linear equation, D is a variable. But A, B, sigma and sigma E, sigma A are the variables, are not no more the variables. These are the constant that can be figured out of the thousands of users training data. So this is this was the one for attention factor. Attention factor, where did we have it? Okay. So it talks about the position, size and contrast of ith element to be placed in such a way that it becomes that the user's attention doesn't get reduced on that factor. So it is about a static model. First of all, it is not a it is not a about a dynamic model. Yeah. Okay, I think Style as yes, yes, yes. Okay. I think we have covered I mean everything from the this week's lecture. I think last week there might be something CMN GOMS model we did not discuss, so that is one thing that we didn't cover in the problem solving section. So these problem solving sessions I have constructed based on the previous year assignment, what was asked, what are the topics that we require to answer these questions. Same topics, I have seen that they have asked questions on the same thing in this year's assignment as well. Yes, okay. If you want to give any feedback, please post here, or you can check out the video when I post it on YouTube. Please post your comment over there. Yeah, I am uploading all the videos immediately after the session. You get the link 1 or 2 days after this session. And if you have visited the link, you will see that I have created a playlist also. So all the videos are there in the playlist. Thank you. And thank you for joining. Please do join every session so that I have somebody to interactively go through it and I know what are the difficulties or the doubts that are present. Thank you. See you all again. Thank you for joining.